Okay, as you can see, Yale University, Derek Briggs and Associates have accepted mud fossilization, and so now we're going to start examining the soft-bodied mud fossilization. They call it by a little different name, but it is silica-rich oceans that create this mud fossils in the Great Flood. Now, we've been studying at Mudfossils University for 5 years, so we have all the evidence and all of the DNA has been extracted from them, and CAT scans, and I'm going to show you all that in a moment. But they're fully understood now. However, they don't really understand the exceptionally preserved soft body forms, but they don't understand how they got to be this way, and they're preserved as sandstones and so forth. Now, we understand that. We've been doing it for a long time. So I'm going to show you what the evidence for mud fossils is, and I'll show you mud fossils. You can go find them in your backyard all by yourself. All right, this is a selection of mud fossils that's been CAT scanned. It's a human finger. There's no question about it. It's been it's a left thumb, and that's been CAT scanned. And these have all been, well, almost all been CAT scanned. 7 of them. The ones that are important. That's a bone, at the end of a bone now, and it's fully articulated. Hold on a second. All right, and it has all of the cartilage and all where the ligaments invested, and the bone foramens, and all of the soft tissue attributes that they never find on bones. So, and the reason is because these are mud fossils, and they're preserved in wet conditions, and on the surface is fascia, and I don't know if you'd be able to see that or not, but that is the fabric, and then you see all those little tiny holes. That's like a periosteum. You see the stripe on the thing? That it actually has a fabric that wraps around it. See that triangular strap that wraps around there? It's very interesting the way the bone actually has a fabric wrapped around it, and the ancients used to call it tunica. And as a matter of fact, this here, I don't know if you can see that. Okay, yeah, this one right here is a human lung. That was DNA tested. It's a human lung. And it has the little thing on the bottom there that is, you can see that red spot we dug in there to get the DNA out in very sterile conditions, all done correctly, sterilized the tools, all done now. 3 DNA tests were done, one on this, one on a finger, which is here. This is an eroded human finger, and you can see the bone pattern, the phalanges bone black pattern that's inside it. There's your vein and artery there. The artery side glows out. There's the holes, and the end one, all 3 of them. And here's the vein side. Doesn't blow out, but you can see where they were. And there's a triangular investment. They all have the fingers where your flesh invests into it. And this one has the same thing. This, you see these oops. See the triangles there? I don't know if you can see that or not. Oh man, it's heavy. That's a fingertip. See how triangles? That's how the ligaments invest onto the side of your finger, so they can pull it around and do all the articulation your fingers do. Now, you see that I showed you the bone sticking the black. This is the same process where the iron inside of these leached through this organic matter, and there's iron inside of bones, which is what's called ferritin, leaches out. Now this is a fingertip. I saw you. I had that with the garnet. Let me see if I can find it. Here. Now this is a fingertip, and it's some kind of primate because they had a fingernail. Now the tip, you see, that's a garnet sticking out there. It's all garniferous. All that red stuff is garniferous, and that is extremely common in virtually everything garniferous. It's all the little blood, and this is the fibers of the skin where the silicon fibers were, and on the very end, I don't know if you can see it or not, but there's a vein and an artery. See that one on the, whoops, you see the one on the left there? It has a a little brown one there with a little dimple sticking out of it. That's what's called a vein valve. And that's what the clamp is. And the brown part is a vein blood. And then on here you have a clear one that is the arterial side, and they blow out because there is no clamps in arteries. And what happened, you see it eroded away a little bit, but you can see this channel of where the nerves ran and where the bone was and all that. But what happens is bone is CaCO2, a CaCO3, but it's calcium, which is calcium plus 2, or it's got 2. It wants to bond with almost anything. Let me put it that way when it gets wet. So let's just go with that. That's why they find bones in the dry places. You don't find bones in the wet because the bones are the ones that erode. The skin gets plated because of the silicon and the oxygen, and when it does, it seals it up, and then you end up with these kind of mud fossils. And I mean, I got lots and lots and lots of them, because you do too. You go out in your backyard, you find them in 15 minutes. All right, this is the must-see part 1, and then there will be a part 2. Now, this is about the conditions and some information about mud fossilization, why it happens, where it happens, how it happens, when it happened, a whole shooting match. So you have to start here, and then the second video will give a little more detail. Now, the whole reason for mud fossils is because it's wet. It's quick, cold, wet. Silica rich, which is mud, and not dry ever, never gets dry. And it's wet soils, and the reason they don't rot away is because it's cold, it's wet, it's compacted, and in cold, wet conditions, they create what's called electrical potentials. It's called telluric currents, which is electricity due to the fact that water is a polar molecule. It moves through these tiny muds that are literally 1 or 2 atoms, just a couple of atoms bonded together, and the water can squeak through there, and it creates electricity. It literally does. It's fully understood. Now, in your skin, it's dense with silicon, because that's the strength part of the fabric of your skin, so you can grab things and so forth. Now, that silicon bonds with what's in the water, which is oxygen, O2, which is part of the H2O. The hydrogen gets liberated or bonds with something else, and you get, because that's its most stable form, silicon dioxide. It's sand, SiO2. So now there's your sand, which erodes away, which is the skin, literally the skin. It erodes away. What's left under there? The flesh, the organs, the bones, the tendons, the connective tissue. That is mud rock. It's literally mud rock. You see these rocks that look like mud, and if you look at them closely, you're going to find veins and arteries. Now, then what you have bone and tendon, which is the calcium CO3, which is your connective tissues and your tendon and your bones. And they include kaolin clays. Now, the CaCO3 is what's called porphyritic basalt limestone, which has all these fibers and things in it. They think it's volcanic. It's not. It has nothing to do with volcanic. It's from tendinous material, which is your body creates that. It's a mineral that's what's in your body's calcium. And calcium is your bones. Calcium carbonate, CaCO3, and it has kaolin clays, which are the skin cells. Kaolin clay is skin cells, and which is the little fleshy fascia that is in that area. And so you have your basalt, which is the limestone, which is all fibrous stuff in there. It's not volcanic. It has kaolin clays. Marine limestone contains exactly the same thing, but no kaolin clays, no fibers. It's just the CaCO3, which is the shells of creatures, marine limestone. Now, What else is in creatures? Well, there's blood and bodily fluids, and that is literally garnets, and they come in every single color, but everybody likes the blood red ones. Well, after the blood red ones turn blood red and are, and I have some here, as a matter of fact, I'll find one maybe and show you, but squirting out of the end of a finger. Now, that is bodily fluids, and they create a pattern of crystallization which creates gems. Now, what controls all of these things? Conditions. Conditions, conditions, conditions. If it's near a volcano or near, it's totally dependent on pH, how quick it was encapsulated, what the temperature was on encapsulation, how deep it was encapsulated, what they call solvomorphic, the solvents in the water that come down through there, because it's all because of wetness. Now, when you go to these dry areas where they look for bones, in a totally wrong place. I mean, they look for bones, and that's all they're going to find. Scraps. There's no flesh and tissue on these things. They're finding things that were leftover, scrappy bones that were in dry areas, and in dry areas they get invaded by little bacteria, and they eat every single thing there is until they get down to the calcium and the carbonate, CaCO3 bone. And so they think everything has to be a bone that's preserved. It's absolutely the opposite. Everything that's preserved is preserved in wet condition. Everything that is not preserved is where they're looking. That's all I can tell you. It's a fact. All right, so that's a little introduction to what mud fossils are about and how they are how they come about. Now, you can see that I have a whole batch of stuff here, and we'll go over all these things, and I'll show them what they are and how they happen to occur in these conditions. Because lungs can be in, you can have a lung like this. You see this? You can have a lung like that. You can have a lung like this, which has everything all the way out to what they call the pleura. You can have one like this, which is partially, the pleura is eroded off of the part of the lung that does the respiration. You can have them like this, that they started leaking blood out. The black and red is the leaked blood out of a lung. That's where the lung invested into the body. You can have them like this, that have the actual back and the bones still in the back a little bit, and the lung here, and the lobes showing here because it eroded from the top. You can have them like this, that gush blood out of here, and this literally gushed blood. I mean, I can show you, it literally had, every one of these dots had blood, actually a ball of blood coming out of there. And you can see, as soon as I put water on there, you see how that reds up like that? Blood rehydrates. And that's the whole beauty of transition molecules, and they don't understand that. I think they just don't understand it. That will turn red again to blood. That is the nature of transition molecules. And if you hit them with a little bit of acid, they turn right, the blood just leaches right back out of them. So this is the way we can get DNA out of these things, and it's just what happens. So, we need to take a look at it and study them a little further. And I'm going to show these in a little more detail. Thank you.